So the title of my research is Time-Matricized Triangulation Modeling for Space Traffic Management. So basically I would be presenting a triangulation model that finds its usage in the integration of airspace and orbital space. So let's begin. So to begin with, what is triangulation and how it is used in space engineering? Triangulation is the tessellation process that involves the establishment of polygon patterns. Now obviously these polygon patterns are subdivided into numerous triangle patterns. Let's go to the next point. The triangulation procedure encompasses the computations of linear magnitudes with their equivalent angular measures. So basically this point details that triangulation establishes relations between the angular magnitudes and linear magnitudes. So basically on one side we would be having kilometers, meters as units, and on the other side we would be having degrees, radians, other units. So now comes the nodal confluence. The nodal confluence is identified with the locales that are either located in 2D plane or in 3D plane. So this depends on the problem statement that whether the locales are in 2-dimensional plane or 3-dimensional plane. Since here we are concerned with the space, so we would only be using 3D plane as a general norm. Now come the sides of the polygon patterns, which denote the distances between the established locales arrangement. So basically the nodals would be the spacecrafts and the sides of the polygon would be the distances between the spacecrafts. Now let's move to the next slide. Now here are the applications of triangulation. Navigation and astronomy are the primary applications of triangulation. Apart from these two, engineering metrology, oceanography, geodetical analysis, computer simulations, and robotics are some of other applications of triangulations. Now comes the triangulation criteria in space traffic management. So the first is the space tessellation in three-dimensionally dilated coordinate frame, identification of vehicular traffic as nodal conflux, rendering of polygon configurations in three-dimensional spatial cuboid, rendering of interspatial lines. Now these interspatial lines are again the distances as relative distances, rendering of interspatial angles as relative angular measures. Now after all this, obviously there is privilege for fault correction, data gathering, and finalizing the triangulated mapping. And when triangulated mapping is done, time-matricized modeling of the map data would be employed. Then comes the strategizing neighboring traffic movement, and finally the adjusting of overall traffic setting. So this is the main criteria for the space traffic management. Now here's the image that shows the triangulation criteria in space traffic management. So basically here what you can see is a line of interspace, which is the distance between the aircrafts or spacecrafts. time matrix, direction of flight, angle of proximity, interspatial angle. And the last thing is the circumjacent polygon. So all the yellow lines are actually forming a polygon which is circumjacent, and inside of it is located a spacecraft. Now this all the other spacecrafts located on the circumjacent polygon are actually enveloped around the spacecraft which is located inside of it. So now let's move to the next slide. Here's the road versus air versus space traffic system. Now in the next few slides we would be covering the difference between the road, air and space traffic systems in order to understand why space traffic system is much more complicated than road and air traffic systems. So let's get started. So first is the road traffic system. So here are some of the features of road traffic system. So the first is single layered lattice plane. Now the traffic is sitting on a road and it is not flying. So there would only be one plane associated with all the traffic. So here single layered lattice framework is what we require. Next is linear traffic motion. Now for the most dominant portion of road traffic is the linear movement. Obviously there are angular movements too, but they are not very well dominant. Next is horizontal movement only. Road traffic does not feature vertical motion. All the traffic is moving in a horizontal direction, either forward or backward. And then there is obviously the rear curvature movement, because the traffic features linear path most of the time, so there would be less chance of curvature movement. So now comes the air traffic system. So it features step layered lattice instead of single layered lattice. Now this configuration is because aircrafts are flying. They are not located on a single plane. Some may be located at another plane. Another feature is linear motion with minor angular traffic motion. Spacecrafts may maneuver at some times. The last feature is the horizontal movement, vertical movement, and diagonal movement. So basically all kinds of movements are associated to air traffic system. Now here is the space traffic system. As you can see, it features multi-layered lattice plane configuration. In space, traffic would be transposing in nature, so obviously it would be multi-layered. Next is the linear and angular traffic motion. So linear as well as angular motion would be expected from the traffic, and there would be horizontal movement, vertical movement, as well as diagonal movement. This feature is similar to the air traffic system. And the last one is transposing traffic, which it would be for an observer. Triangulation modeling for space traffic management. Now here the interspatial lines denote the distances. Interspatial and proximity curvatures denote the angles. The unknown variables are computed accordingly, and the data stored in the avionics is obviously utilized for future adjustments. Now let's move to the next slide. Here is a brief mathematics. So here is a So basically the rocket located in the spatial frame is recorded to have a velocity vector of Vr with a time of Tr. Similarly, the velocities for the fighter aircraft and cargo airplane are Vf and Vc. Now the acceleration for all the three vehicles is evaluated as given. Now I would not be explaining much about this because of the limited time. Now let's move to the next slide. Now it is the time-matricized triangulation criteria in space traffic management. So the time matrix is used in conjunction with triangulation mapping, and it is to be employed when the aircraft is positioned inside a 3D circumjacent polygon, as it can be seen in the right side image. There is a spacecraft and it is located inside a circumjacent polygon. Data should flow from the nodes located on the perimeter of the polygon and is to be received by the spacecraft located inside the circumjacent polygon. So this is the time-matricized triangulation criteria in STM. So let's move ahead. Time-matricized modeling in STM. So here's the identification of nodal data from the spacecraft located in the circumjacent polygon, matching the data with the present conditions. Then there's trajectory correction, speed correction, and other system manipulations. And finally, analyzing how the polygon pattern shifts with respect to time for flight safety. Now we'll move to the summary of the whole research. Number one is about space triangulation procedure, which is the establishment of relations between the linear magnitudes and the equivalent angular measures. Space traffic is more complex than air and road traffic systems because of the existence of multi-layer lattice plane configuration. And the last point is time-matricized triangulation modeling, that is to be incepted for a spacecraft which is entrapped inside a circumjacent polygon, which is for the safety of the vehicle, and relying upon the triangulated harmonization of the time-stranded transposing vehicular traffic, the integration of ATM and STM could be executed successfully. Thank you very much for listening.